Welcome to Mexico. Dr. Yuichiro Tanioka is currently professor at the Institute of Seismology and Volcanology in Hokkaido University and Vicepresident of the Seismological Society of Japan. Dr. Yuichiro Tanioka graduated from Osaka University with a bachelor's degree in synthetic chemistry. Then he moved to the USA in 1991 to complete his master's degree in geophysics at Louisiana State University. Later, he studied his PhD in geology at the University of Michigan, where he completed his doctorate in 1996. He was a researcher of the Meteorological Research Institute in the Japan Meteorological Agency, JMA. From the 1996 to 2003. From 2003 to 2009, he was an associate professor in the Institute of Seismology and Volcanology at the Hokkaido University. Since 2009, he is professor of said institute. He has been director of the Institute of Seismology and Volcanology of Hokkaido University twice, from 2010 to 2013, and from 2016 to 2017. Since 2016, he has served as Vice President of the Seismological Society of Japan. So please, Professor.
Good morning. Thank you very much for inviting me to come here to speak about tsunamis and earthquakes. And yesterday I arrived here, beautiful city in Mexico, and I'm very happy to be here. Thank you very much. Today, I try to speak about the tsunami early warning system in Japan, also in Central America, and also somehow in Mexico, how to deal with that. The most recent research we done for those. Because I was involved to establish the tsunami early warning system in Central America, but not in Mexico. This Central America means that Guatemala, Honduras, El Salvador, Nicaragua, Costa Rica and Panama. So those countries, right now, they don't have a good tsunami warning system. We try to establish the tsunami early warning system in there, and I try to help them. So I'm a little bit involved with that, so I'm a little bit talk about that. And then try to discuss about the tsunami early warning system in Mexico. First, maybe it's difficult to see, but here is the Mexico coast, and this figure is taken from the journal of Professor Campos. She's in here, and she will talk about her stuff in the afternoon, I guess. And this picture was taken from her research. It's very difficult to see, even me, but there are large earthquakes occurred in, I forgot the name for this region, but there's one in here is 1936, and one in here is 1980 what, I forgot. And there's a 1733 or something like that, large earthquake occurred in here. And Oaxaca, there is a so-called seismic gap to have a new, large earthquake in this region. And the most recent one occurred in here, last year in February, there was a magnitude 7.2 earthquake, which is not large as magnitude 8, but that occurred in here as a plate interface earthquake. And last year, September earthquake occurred in somewhere in here. That was not a plate interface earthquake, which is causing large tsunamis. But that was an earthquake occurred in here. It's a little bit deeper. So it does not cause a tsunami, but that causing a huge strong motions and causing a damage in Mexico. But the tsunamis only making large tsunami in shallow earthquake occurred in a plate interface, such as February this year. But the magnitude was small, so it's not so big like the tsunamis. So that is the situation in this Mexico. And this is another figure, also Professor Campos. And the earthquake was, you know, the mechanism of the earthquake, and the earthquake was an understress earthquake, occurred at the depths of about 20 kilometers. In this year, February earthquake. That occurred in here, and this is showing the depths of the plate interface. Plate interface means that Cocos plate is subducting underneath, and that the depths of that contours. And the contour showing that the depth of the plate interface is about 20 kilometers, which is same as the depth of the earthquake. And that say that the earthquake occurred in a plate interface. So those earthquakes create large tsunamis. And if the magnitude is much bigger, like a magnitude 8, that can cause a huge tsunami in Mexico, the coast of the Mexico, such as Oaxaca and these areas. So that's quite interesting to see that that kind of earthquake occurring here. And those are the regions to have a large earthquake. One of the characteristics in the Mexico subduction zone is that the distance, here is a trench along the coast of the Pacific coast of the Mexico. The distance from the trench to the coast is quite small. Here is less than 100 kilometers, like 50 or 70 kilometers. Here is only 100 kilometers. This means that when the earthquake occurred in this region, tsunami arrived very quickly. In Japan, I will show you next figures. It's not next figures. In Japan, there is a trench around these areas, and our island is somewhere in here. The distance from the trench is about 250 kilometers, much longer than the Mexico, which means that the earthquake occurred near the trench, then caused a tsunamis. Arriving at Hokkaido, along the coast in Japan, is about 30 minutes it takes 30 minutes or 40 minutes. But in Mexico, it's very close to the trench. It means that the tsunami, when the earthquake occurs, tsunami arrives at the coast much faster than Japan. It means that it's quite dangerous. Whenever the earthquake happens, tsunami arrives to the coast very fast. So you have to be careful. That is the situation in Mexico. Now, first I am discussing about 2011 Tohoku earthquake occurred in Japan. After that, we re-establish more quick and more accurate tsunami early systems, try to establish more accurate early because that earthquake causing a huge damage in Japan. And I will discuss about those first. Then I will talk about tsunami early warning system in Central America, which is I'm involved. Then I will discuss about in Mexico. As I told you before, the large earthquake, 2011 Tohoku earthquake, occurred in Japan, and the magnitude was 9.0. The tsunami height, maximum tsunami height was 40 meters along those Sanriku coast. And about 20,000 people was killed. And because of that earthquake happened, before that, we already have a tsunami early warning system, and it works quite well. And the people also can evacuate in those areas from the highest places. But still, we had a 20,000 casualty from these earthquakes. We have to deal with those. So what we did, before I talk about that, the tsunami early warning system in Japan at that time in 2011 when that earthquake occurred, JMA issued the tsunami early warning about 3 minutes after the earthquakes. So the tsunami didn't come at the coast yet. At that time, there was a warning around those areas, tsunami warning around those areas, and the large tsunami, they said that the large tsunami will come to those coasts. And also, tsunami early warning system for tsunami arrive at those coasts too. So it works to have a early warning works. But the height of the tsunami was underestimated a little bit. Like first they say that the 3 meter to 6 meter. Then they changed their issue and more than 10 meters. But the first issue of the tsunami warning was a little bit underestimated. But still, they issued a warning about 3 minutes after the earthquakes. And this shows difficult to see, but one of the town in Japan coast, blue line, blue areas showing that the inundation areas by tsunamis. So the inundation area, here's the coast, and the inundation, tsunami inundation, the farthest they go is about 6 kilometers from the coast. So the tsunami inundated from the coast about 6 kilometers. And 2 kilometers away from the coast, tsunami height was 15 meters. So you can imagine your coast is maybe about 2 or 3 kilometers away, right? So the tsunami from the coast to here is about 7 kilometers. So 15-meter tsunami, even in here, 15-meter tsunami come. That's a huge tsunami. And people doesn't know because you are in here far from the coast about 2 or 3 kilometers, even like 6 kilometers. Even though the tsunami warning was issued, you think that this place is safe because it's too far from the coast. But actually not, because tsunami comes from the coast 6 kilometers. And we have to issue the tsunami warning, say that those people living 3 kilometers away from the coast, they have to evacuate. That is we need to do. The people in here to evacuate to the highest place. So, not only a height of the tsunami, the issue, the tsunami warning area, tsunami inundation area is quite important. But that's quite difficult to do it. This is a picture showing that areas. It may be difficult to see, but there are a lot of destruction. There was many buildings in here at that time, but all of them are destroyed. And this is also show the pictures of that town, which I show. And you can see that the one of the tree in here was lifted, but all of the houses are completely destroyed by this tsunami. That's very difficult to see too. And after that, in Japan, we put many sensors in a sea actually. This is ocean bottom pressure sensors. We put ocean bottom pressure sensors in a sea, in the bottom of the sea, and connected by cables, so that those pressure sensors can observe tsunamis in a sea. We have 125 sensors right now in Japan after that earthquake happened. The government put the money and put many sensors on the ocean bottom. So now we can observe the tsunami in our oceans, deep oceans, like 2,000 meter oceans. We can observe the tsunami. If we can observe the tsunami at the ocean, then using that data, we can issue the tsunami warning. There are another networks of ocean bottom pressure sensors, which is in the western part of Japan. This is so-called DONET. We also have those in Japan after 2010-11. Actually, the one of the sensor was before, already we have in here before 2011, but another sensor was installed after 2011. So after 2011, we have many sensors now in the ocean bottom. And I will explain a little bit about how that the tsunami generated by large earthquakes. When we have a large earthquake like Japan in 2011 in here, the earthquake, huge earthquake, has a dimension of like a 500 kilometers to 200 kilometers. Here is about 500 kilometers along this direction, and here is about 200 kilometers in this direction. So the totally in this area was moved by the earthquakes. And when the earthquake happened and the fault was moved, ocean bottom was deformed and ocean bottom go up and down by the earthquakes. When the ocean bottom go up and down, the ocean surface also go up and down. So when the ocean surface go up and down, you cannot say to the water to stay because the gravity affected the waters. So the water try to come back to the same places. That causing a tsunami. So that tsunami propagated through it and then affected the coast. So whenever we know that the mechanism of earthquakes, how that the fault was moved, then we can calculate the ocean deformation, ocean bottom deformation, we can calculate the ocean surface deformation, then we can numerically calculate the tsunami. That is the way how to tsunami calculation work. But when we have so many sensors in the ocean bottom, now we don't need to do anything about those kind of stuff. Calculating earthquake and calculating ocean bottom deformation and ocean surface deformation, because we observe many sensors, tsunamis directly. So we can calculate, begin from here to calculate the tsunami much faster or much accurate than those calculations. That is, we establish. This is just a technique, so you may not need to understand, but we can calculate we can calculate from ocean bottom deformation to tsunami, but we can use the data as an initial condition to calculate the tsunami begin with. Using this kind of information, when you have many data, like ocean bottom network, we can calculate a waveform from there. And we just tested the tsunami calculation using those techniques. When earthquake happened in Japan, like a length of 250 kilometers and the width of 150 kilometers, this is the magnitude of like 8.5 earthquakes, and the slip amount of 10 meters, the huge earthquake occurred in the ocean bottom, and we calculate the tsunami from that event. The red part is higher tsunami, and the blue part is lower tsunami. So go up and down the ocean surface, and the tsunami is now propagating toward Japan. This is you can do previously by using earthquake information to calculate the tsunami. Now we have a sensors in Japan, ocean bottom sensors in Japan, not doing this calculation, but also it's difficult. We can use the ocean bottom pressure observations, calculate the tsunami, only using those data, not using earthquake information. You can still calculate the tsunami. And this is the synthetic test to calculate the tsunami only using observation data of tsunami. And this is actual calculations from the earthquake information. And if you compare those two, it's quite similar. So the system is warped. And now we compare the tsunami waveform at several places, like from 1 to 7. And the waveform at here is actually calculating from the earthquake information. And system in here is showing that the waveform calculating from the observation itself. And that the waveform are quite similar. You may see those waveforms from here to here is quite similar. So the method to calculate that tsunami is warped. So let's try more realistic synthetic test for 2000 Tohoku tsunami. And this is one of the source mechanism of the 2011 Tohoku earthquake for the motion of the fault. And the motion of the fault in that part is very big, so that the ocean, from here, we can calculate the ocean bottom deformation. Ocean bottom deformation as like this. And this causing a tsunamis. So we can calculate from here the tsunamis. That is using this information to calculate the tsunami. Again, the red part is go up and blue part is go down. So that is the part of the tsunami we calculated. Let's see if we have information about the ocean bottom pressure gauge. And here actually calculating from the source of the earthquakes. But this one is just calculating from observations at the ocean bottom. So you can see it's very similar. So the system works. If you have an ocean bottom pressure sensor in the waters, we just can calculate from that to the tsunamis. And that about 600 seconds after. So 10 minutes after the earthquake, we can still calculate the tsunami like this and that. Oops, difficult. And then we can compare the waveform at several places, the waveform are also similar. So the method worked. Now, since we can calculate tsunami from ocean bottom pressure sensors, now let's try to forecast to calculate the inundations, some cities. And to do that, actually, tsunami inundation calculation is time consuming. If you want to calculate the tsunami inundations in these cities, you have to have a very fine grid system. And if you want to compute the tsunami inundation in these cities, it takes like 2 hours, 3 hours for recent tsunami computation systems. And that is not enough for the tsunami forecast, because tsunami arrive here is about 10 or 20 minutes, maybe 30 minutes after the earthquake. So we have to be calculate much faster, but that's difficult to do it right now. In the future, you can. But to do that, what we done was pre-computed the tsunami database. We did, because when we calculated beforehand, then we can just choose the inundation from the best scenarios from that database. So we did a calculation, huge calculation of the tsunami database for one cities, and pick up the best scenario for that cities from that tsunami scenarios. That is way for when we did a calculation for this, and then the tsunami inundation database, we pick up the best one from that scenario and try to put that tsunami inundation was the best one. Actually, this is the tsunami inundation along that one cities in Japan. So this is actual calculations of the tsunamis from the source, earthquake source. And that is inundation we calculated from that source around those areas. But to do this, take like 2 or 3 hours. So it doesn't work for the forecast. And this one, we calculated from actual observations, tsunami observation, to calculate the tsunami. And that is the tsunami inundation calculated from that calculation. And this takes also 2 or 3 hours. So it doesn't work for tsunami early warning system. But this one is taken from the database. So this calculation only 6 minutes. So 6 minutes is good enough for tsunami forecast. So after the earthquake happened, and if you have a large ocean bottom pressure sensor in Japan, then we can get this information after 6 minutes after the earthquake. And the inundation is quite similar to this and that. So that system works for the tsunami early warning. And those are the different cities. You cannot see, but here is the tsunami height along those areas. And observed tsunami height for 2011 is showing in bars in here. And the dot are showing that computation. So the tsunami computation and observation are, thank you, working quite well in those areas, right? This is one of the cities which I show in early times, like a 6-kilometer inundation was occurred in Sanriku areas. And you can see the observation and calculation is quite similar in all of the cases. So this system works, this method at least works for tsunami early warning. And the calculation for this and that is very similar. And that is actually the Sendai Plain. Sendai Plain in Japan. Actually, there is an airport in here. The airport was completely inundated, actually, the Sendai Airport. And that's also creating the similar calculation. So this is using ocean bottom pressure data and also tsunami database. So that the 6 minutes after the earthquake, you can issue those kind of inundation in using this method. So that is a method we developed after 2011. So if you can use this method, you can issue the tsunami warning for the inundation in like 6 minutes after the earthquakes. And issue the warning like smartphone using this kind of technique. And if you click that, then you can say somewhere you are living somewhere in the city in here, you click that, then you can see the tsunami height at here is about 2 to 8 meters or something like that. If this kind of system works, then it's very important to see that to help the evacuation for the peoples, even in here, right? But the problem is that in Mexico, you don't have such a system in the ocean bottom pressure sensors. 120 or 200 sensors in Japan, but not in here. So we have to use some kind of adjustment. So the conclusion in Japan, it works because we have a very big sensors. Now let's talk about tsunami forecast in Central America or Mexico, which does not have those kind of ocean bottom sensors. First, in Central America, like Nicaragua, we have a huge earthquake occurred in Nicaragua. Not a huge earthquake. Earthquake was not so strong, but in 1992, there was a so-called Nicaragua tsunami earthquake. Magnitude was 7.6 or something. But the huge tsunami destroyed many towns along the coast of Nicaragua in 1992. This is so-called tsunami earthquake. The earthquake was not, shaking was not so large, but the tsunami was very big. And this kind of a type of the earthquake occurred in those areas. And that is difficult to predict using a tsunami height was difficult to forecast because the shaking was so small and the magnitude, the estimate of the magnitude is underestimated and the tsunami height was underestimated too. And at that time, we have also this kind of earthquake, which that the shaking is very small, but the tsunami height is very large. And the forecast tsunami height for those earthquakes are very difficult. And we have to deal with those kind of earthquakes in Central America too. And we tested our method for those 4 earthquakes occurred in Central America, and 1992 and 2000, it's difficult to see. But there is a 2012, I guess, there was another one, another tsunami earthquake occurring here, and another 2 earthquakes occurring here. And one of the characteristics of those earthquakes, tsunami earthquake, which the shaking is very small, but the tsunami is very high, occur very close to the trench. And this is showing that the cross-section of the plate, cross-section at Central America, and the Cocos plate is subducting in this, and here is the Central America part, and here is a trench, and the plate interface is along those areas, and the tsunami earthquake occurred very close to the trench, meaning that if the earthquake is very shallow, you can say that that might be a tsunami earthquake. And so we can deal with the location to find out tsunami earthquake or not by using the earthquake location. This is difficult to see, but this is the magnitude. That is the energy to magnitude ratio, which means that the energy is very, very small compared to the magnitude, means that the earthquake was plotting in here has a characteristic of the tsunami earthquakes. And the 1992 Nicaragua or the other earthquake like 2004 Java or some tsunami earthquake plotted in here has a characteristic of large tsunamis. And those earthquakes occur very close to the trench. So when the earthquake location, if we know, then we can say that that earthquake might be a tsunami earthquake. And this figure shows so-called rigidities in a y-axis and the depth of the earthquake and very scattered plot, but actually rigidity where the earthquake occurs is actually less compared to the deeper part of the plate interface, which means that the rock in the near the trench was squeezed very easily than the earthquake and the rock in a deeper part. So the squeeze very easily means that the height of the tsunami might be bigger when the very small force to make a rock to deform, right? So here, the low rigidity means the easy to squeeze. So the tsunami height might be bigger. So using those small rigidity, you can adjust that strip amount or height of the tsunamis. That is why we use those rigidity differences for tsunami calculations. This is just an equation, so it's not so interesting. But what we did is, we don't have a pressure sensors like Japan in those Central America. So instead of that, we try to use the location of the earthquake to find out what kind of earthquake occurred. And especially using low rigidities to calculate the tsunami ocean bottom deformations that can make differences of the tsunami earthquake and the typical large earthquakes. That is what I show in here. Using a low, rigidity is lower in the shallower depth and the bigger in a deeper depth, and that causing the differences. We applied this technique for 1992 Nicaragua earthquakes. And here is a Nicaragua earthquake occurred, and the earthquake mechanism was found using seismic data. And this road, we determine seismometers to find the depth of the earthquake. And depth of the earthquake was about 10 kilometers. And using that rigidity to calculate the slip amount and calculate the tsunami inundation along those areas using numerical simulations. This is difficult to say again, but that is the calculation we did toward the tsunami inundation at some town in Nicaragua. And that is actually the observation at that town. The observation and the calculation is become very similar. Even though the tsunami earthquake, which is shaking is very low, but the tsunami was very high, this system works again. And other areas also it's work. So 1992 Nicaragua earthquake, which is very unusual earthquake, but using a rigidity differences you can use for those and calculate the tsunami, and still we can get a good result for tsunami forecast. Other earthquake also works. And this is another earthquake. It works too. So, tsunami early warning system in Central America using a depth-dependent rigidity curve and use a seismometer to define the earthquake mechanism, then using a tsunami database, it takes only 6 minutes. And we don't use ocean bottom pressure sensors like in Japan. We don't need to do that. But using a seismometer, it works for Nicaragua case. This is difficult to see, but they show the tsunami waveform at those. But now, let's think about Mexico. As I told you the first, the subduction in Mexico is quite different from Japan or Central America like Nicaragua, because the trench is somewhere in here and your coast is very close to the trench, about 50 to 100 meters, 100 kilometers. It may work using a Central America technique, using seismometers, define fault mechanism, and using a depth-dependent rigidity curve to predict the inundations. But in this case, it's very close to the trench, so it may be better to work using a GPS sensors actually. Because Japan, the trench is very far. GPS sensor is on land. It doesn't work because it's too far to find the mechanism in plate interface. But in Mexico, GPS sensor might be very useful to predict the tsunami warning, because I guess like UNAM has a GPS sensor along the coast. Like this triangle shown by Professor Campos is the GPS sensors along the coast. So using those GPS sensors to find out the mechanism of earthquake might be very quickly can done. And using that information to predict the tsunami early warning is the one thing you can do for in Mexico, because the trench is very close to your coast. And this is Japanese case, Japanese earthquake 2011. We have a GPS sensor in Japan, the very dense network in Japan. This is about 1,000 GPS sensors in these areas. And using those GPS sensors, try to find the fault mechanism as quickly as like 3 minutes. They can find out the fault mechanism very quickly using those GPS sensors. And if you can find those in like 3 minutes or 6 minutes, you can use database analysis like as I as I show you, and to predict the tsunami early warning, tsunami inhalation warning can be done because your sensor is very close to the trench, as I told you. And using a tsunami database, we established, using the same method for Mexico, you can predict tsunami inhalation like this in Japan. You can do the same thing for Mexico. If you use a GPS sensor to find out the fault mechanism in 3 minutes, and using making a tsunami database like this in Huatulco, you can do it like this in 6 minutes. So that is a way to do it in Mexico, using a GPS sensor to find out the mechanism quickly as possible, then using a tsunami database to predict the tsunami inundation in those areas. That is my suggestion for doing this kind of research, and doing this kind of a tsunami early warning system should be established in Central America, along the coast of the Mexico in Pacific side. So this is my final figures showing in this presentation. Thank you very much.